This is Module 1, Lessons 9, 10, and 11, Part 2. We are going to look at some proofs in this section. We know that all theorems are proven, and they are proven using our postulates and definitions, and sometimes some previous theorems that we have. So let's go through some of these using our ideal method. The first one here is the proof of the vertical angles theorem. This is one of our favorites, and we are given that 1 and 3 are vertical angles just by definition, and we want to prove that they are congruent. So first thing I'm going to do here is I see linear pairs, so I am going to look at angles 1 and 2, and then I'm going to look at angles 2 and 3. Now, first thing I notice is that angle 2 is shared on both of these. So I see a way that I can connect angles 1 and 2. So let's do our define. Angles 1 and 3 are vertical angles. That's given. 1 and 2 and 2 and 3 are a linear pair. And what that lets us do is we can say that they are supplementary. That is by the linear pair postulate. So what does supplementary let us do? Well, it lets us say that the measures of the angles sum to 180. And that gives us this common piece right here. So we want to use the transitive property and then get rid of angle 2 so that we can relate angles 1 and 3. So this is a very simple proof. Let's look how we put it together. We are given vertical angles. We said that they are supplementary. This is by linear pair postulate. We can write it out or name it. And then we can write our equation. This is just definition of supplementary. And that gives us our common term there. So we use our transitive property to set them equal to each other. And then we just subtract the measure of angle 2 from both sides, because that is just a number. We can treat it like a number, so we use our subtraction property, and we are left with the measure of angle 1 is equal to the measure of angle 3. And then any time that our measures are equal, that lets us use the definition of congruence to say that they are congruent. These two pieces are always available to use together. And there's the proof of the vertical angles theorem. We are now able to use this idea at any time. As soon as we have angles 1 and 3, we can automatically mark them congruent because we have a theorem that proves that's true. Every time we use the vertical angles theorem, we are using this proof right here without having to actually write all of the steps. That was a fun one. Now let's do the proof of the triangle angle sum theorem. You know this is my favorite. So we are given triangle ABC, and we want to prove that the measure of angle A, so that's this guy right here, plus the measure of angle 2, that's this guy right here, plus the measure of angle C, sums to 180. That's our triangle angle sum theorem. So what lets us do that? Well, this is one of those times where we are going to draw an auxiliary line because we need something that sums to 180. We need some angles that sum to 180. So if I draw this auxiliary line here, then I now have a straight angle. And we know that a straight angle is going to sum to 180 degrees. Now the reason for this is we can make this line parallel to the bottom, to the base of our triangle. So we can make those two parallel. So that gives us a transversal right here and allows us to relate angle 1 and angle A. And those are alternate interior angles. And if our lines are parallel, alternate interior angles are congruent. And you guessed it, we are going to do the same thing on this side with this transversal. Extend our line there a little bit. And that is going to allow us to relate angle 3 and angle C. And those are also alternate interior angles. And so I am going to be able to say that angle A is congruent to angle 1. Let's use a different color there. Angle A is congruent to angle 1, and angle C is going to be congruent to angle 3. And if those angles are congruent, that means I can replace them with each other. So let's look at how we're going to do this. I have my line drawn with my parallel postulate. I've used my alternate interior angles, and don't forget that this right here, those always go together. If my angles are congruent, my measures are equal. And then I can use my angle addition postulate to add them up. And then my linear pair postulate to make things supplementary. Now, angle 1 and 2, I'm going to put together here as one big angle so that I can have a linear pair with angle 3, right? Because we need two angles for a linear pair. And then the linear pair postulate lets us say that angles are supplementary. So the first thing I want to do is say 1, 2, and 3 add up to 180. And then I'm going to substitute in angle A for 1 and angle C for angle 3. And then I will have A plus 2 plus C is supplementary, which is our triangle angle sum theorem. So let's look at how we put this together. We start out with our parallel postulate. That just lets us draw our parallel line. And then angle PBC. So that's this new angle that I drew. This is 1 plus 2 here. And angle 3 are supplementary. This is our linear pair postulate. And then I simply use the definition of supplementary to make them equal 180. Now the angle addition postulate lets us say that PBC is 1 plus 2, and then I simply take this and substitute it in. Right? There's PBC. I substitute it in for PBC, and now I have 1 plus 2 plus 3 equals 180. I know that these angles are congruent by my alternate interior angle theorem, and we can put both of these on the same line because they both use the same reason. If you want, you can separate them out. You don't have to. Sometimes it's easier. And then definition of congruence. Let's just say our measures are equal. And then I simply take angle 1 and substitute in or the measure of angle 1, and substitute in the measure of angle A. And then I take the measure of angle 3 and substitute in the measure of angle C. And now I can say that the measure of angle A plus the measure of angle 2 plus the measure of angle C equals 180 degrees. And there is the triangle angle sum theorem. And once again, now we can use this theorem without having to do all of these steps. So that's a very nice one. Now let's use the proof of the alternate interior angles theorem. We used this on the last theorem, the last proof. Maybe we should prove it. So we are given parallel lines. That's one of the requirements for the alternate interior angles theorem. Now we're trying to prove the alternate interior angles theorem. So let's take a look at what we have here. Now I see vertical angles right away, and we've already proved our vertical angle theorem. And I see our two alternate interior angles here, but we can't use those because we don't have that yet. But what I do see is angle 2 and angle 6, and those are corresponding angles. And corresponding angles have a postulate, and you know that postulates are accepted as fact. So that comes in very handy for us. So we are given parallel lines. That's our first thing here, given parallel lines. We can say that angle 2 and angle 4 are congruent by the vertical angle theorem, and angle 2 and angle 6 are congruent by the corresponding angle postulate. And why did we want to do this? Because look right there. Angle 2 is going to connect angle 4 and angle 6. We can connect 2 and 4. We can connect 2 and 6. That's going to let us connect 4 and 6. So very simple proof here. We are given our parallel lines. We use our corresponding angles postulate, and we use our vertical angle theorem, and then we have the common to both of them. We cut out the middleman, and we can say that angle 4 is congruent to angle 6 by the transitive property of congruence, and we have now proved the alternate interior angles theorem, and we can use it without doing any of these steps. This is what is so fancy about these theorems, is once they are proven, you get to use it without having to do all of this. Now those were fun. Just remember, every theorem that we use has been proven. This is just an entertaining little proof here. Not any of our fancy theorems, but it's just fun to do. So we are given that the measure of angle 1 equals the measure of angle 3. Now what does that let us do? That lets us mark them congruent. Why? That's just the definition of congruence. Measures are equal, angles are congruent. And we want to prove that the measure of angle AEC, so let's find AEC, there's AEC, that angle there, equals the measure of angle DEB. So DEB. So we want purple equals green. Well, how do we make purple angle? Let's take a look at purple angle. Purple angle is made up of angles 1 and 2. How do we make green angle? Green angle is made up of angles 2 and 3. I hope you see it right here. Angle 2 is common to both of those. So first off, I see our angle addition postulate, right? Purple is 1 plus 2, and green is 2 plus 3. So I can make purple angle, I can make green angle, and I see that they have something in common. Now, what else is common to both of these? 1 and 3 are the same angle. So whatever angle 1 is, I'm adding angle 2 to it. And angle 3 is exactly the same as angle 1, and I'm adding the same thing to it. So you can see how these are going to be congruent. Now, this angle 2 that is common to both of them, this is the reflexive property, because angle 2 is angle 2 no matter where it's at. So let's look at what we have here. We are given the measures of 1 and 3 are the same, which means, once again, we can say that they are congruent. We may or may not need that, but it's something we have available to us every time. And angle 2, the measure of angle 2 equals itself because of the reflexive property of equality. And then here is purple angle is made of 1 plus 2. Here is green angle made of 3 plus 2. That's by our angle addition postulate. So what am I going to be able to do? I'm going to be able to set them equal to each other and then just use substitution. So let's see how this is done. We have the measure of angle 1 equals the measure of angle 3, that's given, and the measure of angle 2 equals the measure of angle 2, that's just our reflexive property of equality there. So I can say 1 plus 2, look what I'm doing here, I'm adding the measure of angle 2, and I'm adding the measure of angle 2. Remember, measure of angle 2 is just a number. I know that 1 equals 3, and I can add the same thing to both sides of any equation. This is just simply the addition property of equality. I took that top given and just added, it's like adding 3 to both sides of an equation. It doesn't change anything. And then I know that 1 plus 2 is my purple angle. 3 plus 2, there's my green angle. So now, because these two are equal to each other right here, I substitute in 1 plus 2. There's my purple angle, goes into 1 plus 2. My green angle goes into 3 plus 2. And those angles are equal. And that was what we were asked to prove. And I simply substituted these pieces in, right? 1 plus 2 is the same as angle AEC. So there's purple right there. 3 plus 2 is the same as DEB. So there's green right there. I simply substituted in for things I already knew. And I created those things by adding something to both sides, making them what I wanted. So this was a little more challenging to see, but still not too bad. And there's a nice little proof for us. There's some nice examples of proofs. I know these are challenging, but if you use your define and explore and look at your diagram, write down everything you know, do your brainstorming, and then make your outline, writing the proof is not going to be that bad. I know that with practice, you will get much better and they will become much easier to do. Have fun with your homework.